We'd like to welcome you all back from break, and I would like to turn it over to Constance Barsky to introduce our special guest and keynote speaker for today. Constance?
Yes, it's my pleasure to introduce Dr. William H. Smith, University Distinguished Professor at the Michigan State University. I will not go through all that was presented in the information that was provided to you about Bill's extensive experience, but I do want to point out that I first had contact with Bill probably in the 1990s. I was interested in the work he had done in analyzing the TIMSS work, particularly in mathematics, and wondering what was happening in science. So I have followed his work for many years, and his concern about educational policy sort of overlaps with the work I was doing with those of you who might remember physics by inquiry in the 1990s. But one thing that struck me by Bill was his interest in international education. And if you noticed in 2019, in what was sent to you, he was elected as a fellow of the International Academy of Education. And quite frankly, Bill, I'm not sure how many US professors are actually members of that. It seems to me to be quite distinguished to be included in that group, particularly for all you've done with PISA and with Andreas Schleicher from the OECD. And although my interest has been in science, Bill did some work in science in the early 2000s that I think, unfortunately, NSF didn't pick up, but I'm still working on it, Bill.
Good for you.
I still think there's a place for it. So again, it's my pleasure to present Bill Schmidt, who will talk about mathematical reasoning in the next step forward. And perhaps I'll get some ideas for science. Your turn, Bill and Jennifer.
Well, thank you very much. It is my pleasure to actually speak with you again, and thank you, Constance, for the invite. And I turned on my Zoom. You were in the finishing stage of a discussion about mathematical reasoning, which is a perfect segue into what I want to talk about. Because I think the world is now finally recognizing a very important fact. And I see this and hear this from many countries all over the world. And that is the inequality in their countries, the economic inequality is so striking and is taking its toll, in the sense that I read this once from, I don't remember the gentleman's name who wrote this, a philosopher, but he said that people are willing to accept inequality in a society as long as they perceive that the rules are the same for everyone as to how you get to that point. But that when they realize that the wealth and the higher income are going and being parsed out, not because of merit, but because of heritage, that they then wonder and challenge and feel it is no longer their responsibility to follow the rules of democracy. And I think, to be honest with you, that's what we're experiencing in this country and in many of the European countries is the same kind. That phenomenon is now coming to reality as we read daily and in our own country have experienced what happens in terms of when things begin, when members of society no longer think it's important to follow the rules that have been set down in the law. And so what does that have to do with mathematics? Well, I think that many now, economists included, are recognizing that the inequalities in the educational system are striking. And in fact, I've written about that, published about that, and it shows that of the total inequality in mathematics at about 10th grade in this country, that 1/3 of that total inequality is essentially related to the inequitable distribution of opportunities to learn. In other words, it's pretty much the same phenomenon as it is in economics. The richer kids get the better stuff, and the poorer kids are still stuck with doing routine mathematics in the form of just doing algorithms, which they learned back somewhere in fourth grade. And so I think that that recognition now is permeating, and people are beginning to say that what we need in this country and in many of these other countries is a focus on literacy, mathematical literacy. Let it become, which I think it already is, the second great literacy that every child in every society should be guaranteed, so that they have a chance at life and a chance to succeed. Without mathematical literacy in today's world, I think it would be very difficult to move forward into better jobs, a better life. And I think nothing gives us a better opportunity to talk about mathematical literacy because than this pandemic we find ourselves in. The definition, so that you know where I'm going, is on the slide. I'm basically not going to read it to you, but I think the important point there is that, see, the students need to learn how to use mathematics in a variety of contexts, that the schooling they receive opens the door for them to understand that this is not just some kind of schooling exercise, but it lays the foundation for what they need to deal with in the world, and so many more judgments that they're forced to make as future citizens is dependent on that literacy. Decisions about their own economic well-being, decisions related to medical issues that are often tied into quantitative things. How often do I take this medicine? Do I need to do that? Can I skip a dose? All of these things come down in many ways to mathematical, quantitative ideas that you have to then put together to come to a decision. I thought about this as a statistician, which is what I'm trained in, that when this pandemic has been going on, how much misunderstanding is created by the fact people don't understand a fundamental thing, which is what a probability is, or they don't understand various other aspects of number, like when they look and see where their state ranks, and they don't understand that the denominator makes a big difference as to whom you're being compared, and that those ratios are different and for different kinds of observations and different kinds of points to be made. So my point is the whole situation in the world, the way the technology has taken us, and the way just pretty much the rest of the economy and the rest of many other aspects of life are now tied up in number, and that we need a literacy that gives for all kids so that they can use and participate in that society. And that's why I want to talk to you today about mathematical literacy. And of course, reasoning, because it becomes the most central aspect of mathematical literacy. So we have to keep in mind as we talk about this, that mathematics by its very nature has a latent hierarchical structure. It is a discipline that is structured. It is not arbitrarily put together, and that hierarchical structure becomes the backbone of mathematical literacy. I want to make sure up front that no one mistakes my comments to suggest that we can lessen or we can do away with mathematics as it's been taught. We need the foundations of mathematics to be there in order for one to be literate. But what that means and how that comes to the students is what I want to talk about. That foundation needs to be present, but there's more that needs to be done in order for it to become useful in a literate sense. So we have put together a new school, grades 1 to 9 only, mathematics framework to support literacy. And of course, you start with the mathematics content. That's what I was just speaking to, that in effect, that is the foundation and will remain the foundation. And there is no way you can become mathematically literate without that foundation. But what that foundation means and what is included and how much allocation, how much of the time, instructional time needs to be given to which topic. All of that can evolve and change over time, but the foundational ideas are so central. I'll tell you a piece of piece of study that's going to be coming out on June the 15th. I have nothing to do with it other than being an advisor. But have found, I saw this, probably shouldn't be talking about it, but basically they found something very interesting. And I think it really speaks to this literacy and what we're talking about. And that is, it's the eternal search to find those topics in the earlier part of schooling that will produce and support students in their learning of algebra. That many have tried to find that. And of course, fractions becomes a major candidate to be looked at for such a thing. And what we wanted to look at is to see where and how that fits in to the mathematics content. And what we decided was that, yes, in this study, if you look at the results, you come up with a very interesting conclusion. It's not the individual topics. They picked a set of main topics from grades 1 to 5 and looked at them. They had longitudinal data. So it was a good study of something like 12,000 children. And what they found is that none of the individual topics were statistically significantly related to the score of algebra at 10th grade, or no, 9th grade, they gave the test. And what they did find was that a cumulative measure, which they called the foundations of math, that was. So in other words, it is not the individual topics. It has this, the way I interpret this is that total sort of score, if you will, was representing that framework up to that point in time. It connected the ideas and asked for a cumulative understanding of the foundational topics that occur through the first 5 years of schooling. And I think that's an interesting finding that they will have to unpack in other ways and more thoroughly. But I think it speaks to this issue. It's not any one topic. It is the collection in the correct order of topics which develops that kind of literacy that we want to be able to talk about. Our framework includes that content. Also, these are the other things which I'm going to mainly talk about. The fundamental mathematics concepts, math relevant 21st century skills, and I've chosen the word quantitative reasoning instead of mathematics reasoning because I want to make distinctions and allow people to see that this can be done in straight mathematics, but what we call now algorithmic and geometric and statistical are also part of mathematics reasoning. And so in effect, mathematics by itself refers to pretty much the number system and algebra and things of that sort. So that's a major element of this, which is what you were talking about just before I came on. And finally, what I think is the crux, the actual element that is missing when you were talking at the end there about what's missing. I can tell you that I believe from the work we're doing that what is really missing is higher order applications. And I'll define that for you in a moment. But to actually show and have students work with applications, both real world kinds and those in mathematics, or what I call the world of mathematics, and they must be higher order. And that's the key, I think, to all of this. Mathematical literacy is developed through applications in which students have to use the fundamental concepts together with this reasoning, and this is the perfect opportunity for the actual segue into 21st century skills. Not all, and not in some arbitrary way, but in a very logical way. Several of the 21st century skills, I believe we identified 7, and I'll mention those later, are the ones that fit mathematics, that they segue from and into mathematical reasoning and problem solving in real world applications. So that's the framework that we have. That framework, by the way, I was asked to develop, and it is the framework for the new PISA, which should have been this coming year, but is now scheduled for 2023 because of the pandemic. And that framework with those ideas are part of that new PISA. PISA is actually going to attempt to come up with a special subscore on reasoning itself in a way that reflects what we're about to talk about and is not what has been the traditional PISA type problems, which they did call literacy. And this will be another subscore that goes further into what we mean by reasoning. What you're seeing in front of you here is just a sort of a sketch of what I just sort of verbalized to you, where you can see these various parts all intertwine into what we call, what we're calling mathematical literacy. At the bottom of that diagram, that model, you'll see what is and has been in the past, starting in 2012, the PISA format of you have to formulate the problem, you have to then solve it, and then you come and generalize your results. That still is symbolic of the process, but what is above that is what we think needs to be thought of as part of this, and the formulate element, as you will see, becomes a very central feature of this new form of literacy, which actually is in some ways more logical, and that's how it connects to the 21st century skills, a more logical way of putting things together and then formulating it into a mathematical expression and then can be solved. So I think in one way, what we're talking about can be thought of as a pre-step to that first step that's on that model of the PISA past, which is formulate. We think there's a prior step, a pre-step that students need to go through in order to really be mathematically literate. And so what I'm going to do for the rest of the talk is to give you some definitions of the parts of things that we're talking about, and then share with you some examples of what we believe are higher order and how that is, and what distinguishes them from the regular kinds of applications which we see, which are often commonly called word problems. Okay, the next thing actually starts to give you some definitions of what we talked about. One of the things we said is, yes, the basic mathematics remain the same. You need to know what a fraction is. And of course, I would add right away, you also need to realize that one number over another number is ratios, also it's percentages, proportions. That's the beginning of the idea of a fundamental concept that things can spread across, can connect the mathematics, but more on that in a moment. But for the content, we kept in our work, the content to be pretty much the same as it was 20 years ago. Some of you, and Constance was talking about that, the TIMS, the original TIMS study, the third International Math and Science study, the 95 version, had a framework for content. And we thought it would be very interesting to use the same framework, but recognized after we talked with many mathematicians, statisticians, and we had consultants from each of the 4 major economic aspects of our economy, the various subdivisions of our economy, dealing with higher, I can't think of what the word I want. Let me skip it for a second. We were talking about medical industry, communications industry, economics industry and the high-tech manufacturing. That was the word I was trying to get out, high-tech, the high-tech manufacturing. And from all of that, there were 4 topics that were suggested that are going, as the title suggests, looking toward the forward. And we wanted to put these in to see to what extent these were becoming used in the countries. Now, let me speak to the notion of the countries. I'm not going to go into any detail. We're still in the middle of this work, but we did a study, are doing a study of 19 countries. And we have some of the top achievers in all of these international things: Japan, Hong Kong, Korea, Taiwan, and many European countries that do quite well, Estonia, Latvia. And so we're looking and working with them. And so these 4 topics were added as part of the content. Computer simulations towards solving mathematical problems is becoming used more and more on more complex problems. You know, for example, I have some investments in the stock exchange, stock market, and the woman that works as my assistant through the company showed me a computer simulation. For those of you that know statistics, it's unbelievable. They're just simulating various things under various assumptions, and they simulated something like 1,000 times. So they actually get a standard error. They don't call it a standard error. They talk about it as your likelihood of succeeding. But it's a good example of where in the world now, if you really go to your financial advisor and they do this, if you don't have any understanding of statistics, you're not going to have very much of an chance of understanding whether what you're being told, other than what the words are that the person that's presenting it to you does. But when I saw it, I thought, holy cow, this is straight out, you know, computer simulations to solve a problem. So that was one. Conditional decision making. Another word for that is more statistics, that takes you beyond mean, median, and mode into actually how it can be used in decision making. Exponential growth. The whole world of pandemic is driven by that, or is explained by that model. And then the last one are geometric approximations to irregular spaces. I don't know if you've been to Chicago recently with the architecture that's there on these buildings. The forms and the shapes of these would drive anybody nuts in trying to figuring out the geometric approximations, the sizes for doing things like carpeting in rooms that come to a point and things of that sort. So the whole world of what's being built around us is using many more geometric sort of shapes in their work, and how to approximate numbers from those for various purposes is becoming increasingly difficult to do. So we added these 4 to the other ones that were part of TIMS. And that was in this work with these 19 countries, we looked at what they were doing. I'll tell you, the short version is not much has changed over 20 years. That's the sad part of my message to you. Not much has changed. These new topics, here and there, a little bit here, a little bit there, nobody doing much. It's the same. The actual diagram, if you remember the upper triangular diagram that we had that showed the 3 principles of focus, coherence, and rigor, those still exist. The same. It's remarkable to me how much the world has changed. Technology has changed. The fact that kids carry computers on their arm in the form of a watch and can do all kinds of computations, that the mathematics has not changed. Now, some of it, as I said a moment ago, won't change because there are some fundamentals, but to see nothing really changing and nothing new coming in, the one strong thing that our consultants from those 4 industries, when asked the question, what would you like the future employees, what kind of background would you like to see them have? And secondly, what would you similarly want your customers to have in understanding your product? all four answers were simply statistics in some form, that is being driven and used so much more and is necessary for understanding that was the single most added, sought out additional feature to K-9 curriculum. Now, the next thing is those are just things, but let's talk about this reasoning. And I wanted to tell you that I use the word quantitative so that I could distinguish four subparts: mathematics, which is straightforwardly math. Deductive inference is related to the number system, etc. Theorems, axioms. Computational reasoning has to do with what people call, and sometimes they talk about, large data analysis. This includes computer programming, not the need to teach children a particular computer language, but you can teach them the language of repetitiveness and how you build logic to do that by simply using words and equations they're familiar with. So this is not about teaching them computer programming, but computer design, you might say, the design of a computer program. Geometric is self-explanatory, and so is statistics. So we looked at reasoning in any one of those four areas. And I think I'm going to stop referring to what we looked at in the study. This is what we believe to be the fundamental definition of reasoning, expanded to include these four sub areas. And this is the core of literacy. There's no question about that. If we hope to get our children to an understanding of literacy, then we need to have them experience quantitative reasoning. And that's what I heard at the back end of the conversation I picked up when I came onto your site at about 15 minutes after. So I'm glad to add to that, in that sense of that's so important to the establishment of some kind of quantitative, some kind of mathematical literacy for the students. I want to also now define those other elements of this, and I'm not going to read these all to you, but let me describe to you what we mean by a core concept. Mathematics, as I said, has a latent hierarchical structure where things fit together. And the further up you go, it builds on what preceded it. And so therefore, that structure is what we talked about back in TIMSS, which was missing in the US curriculum. I'm happy to say what I see. It's much more now present in American school math books and school curricula. But this is an idea that, and I want to point out this, that these are not topics to be taught. These are ideas, concepts that sit as the underpinning of mathematics. This is the glue that holds together the multiple topics. This is what's fundamental. I use all those words, hoping one will make sense to you. This is what you can find. You don't teach this, you recognize its existence, such as number systems and their algebraic properties. You're looking to see, and when you encounter a topic that is consistent with the use of these number systems and how they're built and the algebraic generalizations thereof, you point out that this is part of this number system, that this is a very fundamental concept. The very notion of number is a fundamental concept in mathematics. Number not as counting things, but number as a number itself, the number system. And so you connect the various topics you do over the grades, you bring it back to them and make it part of this broader, deeper concept. The idea being that if you understand those connections, you are getting to the point where reasoning becomes more easily done because you know the connections and you can see the problem and the exposure of what you're working on now in relationship to something that you might have had 3 years ago, because you can see the connection. Even though it's calling it something else, you say, oh, wait a minute, that's just like those ratios we used to do. And you begin to then be able to have a deeper knowledge that connects and gives you the tool of being able to reflect on those connections. And you got to build those neuron connections. I mean, they don't happen by chance. The schooling has to develop those, help the students develop those connections of the varying neurons or holding the various things they're picking up in their mathematics instruction. I'll just sort of mention these. The next, we I think have 5 or 6, but the backup one, the other one on that page was mathematics is a system of abstractions and symbolic representation. I teach statistics to PhD students, and they still don't get, some of them, an abstraction and a symbolic representation. So if you use alpha to represent that type 1 error, and you use alpha as the intercept on a simple regression, you would not believe the confusion that brings about. And that is in part because they don't understand the abstraction, the abstract nature of mathematics. And you can represent things with any Greek letter you want. There are traditions, but those are just traditions. The next one is the idea of the regularity that occurs in the structure of math. And this helps you, it kind of replaces those parsing rules that can be done by the computer, and gives conceptual images that try to make this kind of structure much more, being able to see it and recognize that that is an aid to the procedural knowledge that they're trying to learn. In other words, if you really understood these more, computations would be a lot easier for everyone. Next fundamental concept is these 3 here: functional relationship, the whole notion of a function, and what that means. Mathematics modeling as a lens to the real world. And here we now begin to point directly in a fundamental concept to the notions that we're talking about with wanting to be mathematically literate, that they can use this, that modeling, which is a very integral part of mathematics, like a polynomial can be used to give an approximation to any equation. Well, you begin to get ideas of how you then can look at the world and through these kinds of modeling. We can see that if you read and have the background, as you read about the pandemic, and you look at the modeling that was going on revolving around the ability we have now to map the genome. And people are able to use that sense of modeling toward understanding. And I think the more you had a background in understanding what modeling is and does, you would not have one of the things that I watched with great interest is, why do so many people think these are false, what they call false facts, or they're just not right? Well, it's because they don't understand the model. You don't understand that as you improve enlarge the collection of your data, that the model estimates would change. And understanding that a model is something like that, which has a notion of fit, and fit can improve, and all of that would help them understand that that's why those numbers change. Somebody's not making them up just to look better. Those are driven by and understood through the modeling process, which is that fundamental concept. And the last one is to my heart. Maybe that's why I use the word heart. Variation as the heart of statistical inference. If there is one concept that is the most important to undergirding statistics, is the understanding of variation and its partner, covariation. It seems so simple to say that, and I suspect many of you may question my judgment on that one. But variance is what brings about all of things like ANCOVA regression analysis. Any of those topics you hear, that's all dealing with the variation, because it has to do with the fact the phenomenon you're studying cannot be characterized by a a straightforward stochastic model like the concept above it is capable of, but you are dealing in a probabilistic world, and that is because of that variation. And that, by the way, is also one of the hardest concepts for students, even graduate students, to really understand. And, oh yeah, they can write the formula down, but they don't really understand the role that variation plays, and the central notion that without variance, you wouldn't have the relationships they're trying to look for. But that eludes them in many of the students. So those are the fundamental concepts. Those are ideas, again, not to be taught, but they are the connecting tissues that we bring in as you teach mathematics. If you bring these in and identify and refer them back to these fundamental concepts, how what they're learning now is connected to these basic ideas, I think that's, well, isn't that what we call intelligence, being able to connect ideas in your brain and carry on? No, Constance, you may recognize this from science as the fundamental 8, or the 8+1, where we had the same goal of finding 8 fundamental physical principles that explain the world, that again are not to be taught, but they're these separate concepts, fundamental, and which can then be put together to explain phenomena from biology, geology, chemistry, physics, and all the mixtures of those. And it works. That was, Constant was part of us looking at that and trying to bring that out into a greater, but it was very interesting. It's hard to buck tradition, and it never quite caught on to the extent we had hoped it would be. I worked with Joe Kraychek, who's at Michigan State too, who loved the idea, but we still couldn't get any catch on. But Constance, it's written up in a book, and I'll send you the title of the book. And there's a section on both the mathematics stuff I'm talking about and the science. You might enjoy that. So the next basic framework dimension outside of content is 21st century skills. There's a lot of talk about this, that this is what should be done. This is what the world has changed more toward. And these are fundamental things that are not just important to business people, but they're important to people to survive in today's world. And the National Academy had put forth a paper book with a listing of these and discussion of these. They're being discussed at all levels and around the world. PISA is now working in a project called Project 2030, where they're looking at these kinds of skills and how they fit in. One of the problems, I think, that many people that are advocates of the competencies act and present them as if they were separate and isolated from the content of the subject matter they're trying to bring them into. And in fact, some have advocated that these be taught as a separate course to be added to the curriculum. I think that's a ridiculous idea, to be perfectly candid. That would just simply make for an overload. And secondly, it makes no sense. These are skills that can be and have their the strength to the degree to which they can integrate with other subject matters or topics or things that are needing of solutions. These can be embedded in the world of law. They can be embedded in the medical world. It's where decisions have to be thought through and made. These kinds of competencies are the ones that would be an assist. And in this case here, what we're proposing those is another dimension of this mathematical literacy concept. These are things which we believe, and there are only 7, if I remember correctly, of them that we chose from the list of, I think PISA has 25 competencies listed. But these are the ones that we think are natural. And what do I mean by that? What I mean by that is, again, like the fundamental concepts, these are not to be taught in that narrow sense of the word, but connected, so that when you are doing math, you can point out that this is really critical thinking. This is what you need to be able to do in general in life, that their teacher with just a few sentences can expand the concept and help them realize that this kind of work that you're doing with your reasoning in these applications, this is what is part of life. And it's not always with numbers in it. Sometimes it's just straight logical argument that you have to resolve which way to go or which way to develop in your product. And so this is how we believe, those of us that created this, that how this would fit into mathematics, not as separate topics, but things that can be actually integrated into the very coverage of the mathematics as you carry on. And the first one, of course, is the most obvious, critical thinking. And I would make the argument that the kind of things that we're going to call higher order real world applications, by definition, are critical thinking. And they would be the perfect opportunity to give and to show that there are different forms of inductive, especially in geometry, deductive, and mathematics more generally. And this kind of thinking is not only, you can take the numbers away, and it's still a fundamental aspect of how you need to think in order to look at the world in many ways. Creativity, the novelty of it all. Can you think beyond the box? Can you, in mathematics, are you able to look at something and figure out a different way to do it? I'll show you, there is an example of one of those that I have to show you, but that's another one of those 21st century skills that we think is relevant. Again, I don't want to read all this to you. Information use has to do with their ability to acquire the information they need, and using of digital devices is certainly part of that. And it's not just something you do in school. The systems thinking, this is a big one, we think, that a lot of things that need to be solved are parts of systems, whether they're made up applications in a math class or whether in real world you have this kind of thinking that's necessary. You have to figure out what your system is and what's in it and what's not in it. And then therefore you'll know what you can change, those that are in your system. But maybe those that are outside, you have to merely take account of and let them reflect their effect, but would not necessarily include them in the system itself. They're exogenous, if you will, to use that term, to the system. And this, I think, is almost self-explanatory how that would fit into the real world, that the systems thinking, because so many things that have nothing to do with number are open to this kind of thinking. And again, this is not teaching that, but when you are teaching something in math, which is clearly a good example of building a system and so forth, a system of equations to characterize something, to point out that that's certainly a kind of an ability, something that you can do well outside of mathematics. And in that way, we feel the 21st competency skills are relevant because mathematics is a very logically driven and empirically applied and very logically put together, and therefore is a place in which you could see examples of skill of systems, and therefore easily mention how that could go beyond to some world that they might understand. Now, the other couple of that we have, those were all skills that are competencies that are intellectual based, thinking, cognitive kind of skills. These are really more personal competencies. Communication. Can you not only understand what you're doing mathematically, but can you communicate it to somebody else that doesn't know a lot of mathematics? This is a characteristic that is so important. When I don't mean this as a brag, but when the Tims came out, the first Tims, the original Tims, I had the opportunity, the extreme opportunity, to actually brief president on down and a lot of business people and others. And what I learned in that process, because I had a friend, a good buddy friend and a colleague who was had studied communications. That's what his PhD was in. He taught me that first notion of communication, how important it is, and being able to say it in their words and not in your words. At first, when I started, I used my academic words, and that doesn't go very far, let me tell you. But another set of words that are more commonly used are much more well received. So that is a skill, because mathematics is often very complicated to explain, or in statistics to explain the result you have. And you can't go on with all your caveats and expect them to necessarily follow you nor care about what you're talking about. So that's I think, another one that's just natural to go with mathematics. Reflection, think about what you do before you act, and persistence. You know, those math problems, if they're difficult and they really take students not just a few minutes to whip through 20 of them, but that they have one that they sit there and they can't figure it out, and then they go to it next night and they still can't figure it out. They begin to get the idea of that the world is not simple. And as you apply this math literary sense, you will have to sometimes persist in trying to find your system, your model that characterizes what you're talking about. Okay, the last one this just I mentioned about the 19 countries. One good thing is that we found all of these in the standards. There are official curriculum standards. All 19 countries called for these 4 areas. The inclusion of the real world applications we haven't talked much about, but I'm coming to that. But that's good news, is that the coverage of the more futuristic topics. I'm giving you some early examples of the findings. It varied across countries, and it wasn't done very much. We're still stuck without moving much in any direction toward things that are much more relevant in today's world, such as these 4 are examples thereof. The next slide again tells us a little bit more about the study. The standards indicate what countries intend, but we then wanted to look to see, what about the textbooks? Textbooks is still pretty much across the world the dominant instructional tool that is given to teachers. So we figured we didn't have the money or the ability to do a study of the teachers and how much of the things we talked about actually were being done in classrooms in these 19 countries. But what we could do is look at what we in the original TIM study called the semi-implemented curriculum. It's because they may change it, but it pretty much defines much of the curriculum for these teachers. So now we're going from policy, which is what the standards are. We're now going to practice, what the textbooks provide an approach to that kind of practice. So we studied those textbooks, and the results, you'll have to wait. We expect to release these results sometimes in the fall, maybe in November is when the results of this analysis will come out in full detail. The next slide shows that across all the textbooks, there were 20, because some countries ask us to do 2 of their books. Do they do what the policy says, as the title says? No, they don't. The countries specify what they want done, but they don't do it. The books don't do do it, and very likely then I don't. This is my hypothesis. I cannot prove it. I do not have data for it, but they don't do it in the books, and therefore the teachers probably don't do this to any great extent. What we found is across the 25 textbooks that come from those 19 countries, there were two general types of exercises: computational and word problems. That's uniformly, at least across these 19 countries. There's no real different styles of textbooks by country. There are different degrees thereof, but they basically have computational and word problems. The latter is viewed by most as real world applications. When we brought in these country mathematicians and math educators and teachers to help us do this work, their view immediately and instinct was that the word problems are what we were talking about. When we were talking about real world applications, we meant word problems. But our initial observations, again, from the research, suggest very clearly they are far, far from what we mean and what is meant by real world applications. So the next slide actually appeals to the literature. And here's a mathematician, a math educator. His name is Pollock. He was at Columbia University some 50 years ago. After we did this study and we were still just looking around, one of us found that piece of literature 50 years ago. And it was like he had anticipated exactly what we would be looking at. And it is quote, and I put both quotes there because he could say something I would be reluctant to say, that what he found 50 years ago, what we're finding is still summarizes the current situation. He called them silly, he called word problems silly, redundant, and even stupid. That's his word. Those are his words. I probably would never myself write an article with the word stupid, calling something stupid, but that's what he called it. And he goes on to say as it goes on, and I'm going to read this to you. You use words from everyday life outside of math to make the problem sound good. In other words, you always put like apples. Johnny has 7 apples and Susie has 3 apples. You always make a reference to something outside of math in the world and makes it sound good. The key feature, he goes on, is that a certain amount of translation from English to math is required before you start. That's what in that earlier old model of PISA that they call formulate the problem and point presumably to the practice as it presumably is to practice such translation along with practicing the math. You have to do the math after you formulate it. The statement of such problems rarely question the honesty and the genuineness of the connection to the real world, but the connection is often false in more than one way. In other words, what he's saying there is half the time with these word problems, if they're about something that looks like science, they're not really right. They're overly simplified. They're not properly qualified. There is no answer the way the problem is stated. And that many of the times these things are just, well, as you said above, just plain silly and redundant. To the day I die, I will remember that my least favorite word problem. It had something to do with trains, which for some strange reason were on the same track, headed to each other. And there you told the speed and some other stuff, and you had to figure out where they'd meet. And I remember as a kid sitting there and saying, I don't really care where they meet. Why should I figure this out? And I think that's partly what Pollock is referring to. It attempts to pretend to be real, but it's not anything much that anybody cares about in the real world. So now the next slide helps and defines what we mean by higher order real world applications. They're realistic, they're authentic, they're in the real world, but they require a lot more than identifying what math is needed. The problem needs to simulate the real world. It's messy, it's complex. You have to organize, you have to actually figure out what the question is. You have to figure out what's relevant to answer the question. That's what we mean. That's what Pollock meant. He gave an example very similar that would fit this definition in his article. In other words, it's not that the real world is just not a toss in to make it appear to be real world, but it actually represents the real world. You're given several pieces of data, of numbers, of things, and then you're asked a question, you're told to find the fastest way to get to the airport. That's the example Pollock used, and pointed out there are multiple solutions depending on the assumptions you would make. So what we're saying here is that to be a real world, there has to be a point where the student has to say, what's the problem? What are we trying to solve? What do they want to know? And then to aggregate and figure out what data is relevant to the question you've posed. And so that's real world. It is not just formulate, solve, and explain, give you results. It's a figure out. It's the prelude. It's research that we do in our world. The first thing you do is you figure out what your real problem is and define it carefully and thoroughly and meticulously. And that you have to do in the midst of a messy world where things are not always so straightforward. And then you have to figure out what data you need to address that question. And that was our definition. And in our research work, we had to train for 2 days of the thing. We had to train the people to be able to essentially recognize this. Now I want to just show you briefly a few examples of what we're talking about. Now here's a page out of an Australian textbook, and it's the opening chapter for looking at the Cartesian plane and identifying, placing things in the green. And there's no problems or exercise here. But what I like about this is look at that, why learn this? There's your example of a way of beginning to develop the fundamental concept. You're pointing out how this is necessary to model mathematical relationships of varying sorts. So you're connecting this lesson. It's not just a Cartesian product set and how you put things into it, but it's how you use it. What other parts of mathematics does this become fundamental and helpful in dealing with? That's like the fundamental concept. The blue area, which wait, did you change, Jen? We'll go back to this one. Under the forum, look at the questions being asked there. If they're really used in class, like there are other ways to represent the chessboard. It talks about a very practical thing in the world that they may be in. Kids may be actually playing chess at the age of 15, or at the later age stages of middle school. And these questions are the kinds of questions that you could ask and discuss, and you could talk about the answers, which begins to build that thinking of 21st century skills and also the fundamental concepts. Next slide is just another example of the same thing from another book. It's Introduction to the Geometry. And the question is, what do you need to build a better stadium? And they then talk about the strength of triangles in a physical sense. So it connects to the world of construction, of what do you call that? People who design things. I can't think of what you call it. Architect, that's the word. And so then again, you have why learn that and the forum. And this is the Australians' book way of sort of connecting and showing how what you're doing is a practical thing, in this case, chess game, but also goes forward to help understand how it connects with other ideas. I thought this was kind of neat because just recently I watched The Queen's Gambit, which has been very popular in making people think about chess and would fit into this kind of thing. So these are just examples of the way these one book sort of works with these fundamental concepts. Now I'm just going to show you some examples, and I really don't want to read them to you, but you can see that once to go to a store, there's a discount on everything. You have so much money to spend. You know, what are you going to buy and why? Can you make an algorithm by which to determine what you can buy? The point is you only have so much money. And there's a sales tax and there's a discount. And so how much, what are you going to buy and how are you going to do it? And I think that gives you a chance to and write a decision model. You can see you're being asked to go well beyond just figuring out the number described, how many things you could buy. The next one, this one gets, this is, I just wanted to point out, we also, when we did this work, we identified real world, no, excuse me, applications in the math world. And this is one that somebody, what we were talking about a little while ago, you give an equation and then you give, I don't know how many things there are about 10 or 11 different things you could do. And you're asked does that make the equation still true? If you mess with those, if you change, add 3 to both sides of the equal sign. So you can see it's a reasoning to begin to see the pattern of what's happening, what can change and still allow questions, two equations to be equal to each other. Next item is
Bill,
probably
are you cognizant? Excuse me, Bill, are you cognizant of the time you need to be?
Yeah, I was told I could go. What time do I need to be done?
You had 1 hour.
Okay.
So try to wrap things up in the next couple of minutes.
Yep, I will, because all I do have is examples that I want to share. I will just, I'll share this one with you. There's an accident. You're given information. The witness is questionable, and you're given information about blue and red trucks. The one that caused the accident was, I think, blue, if I remember correctly. And then you were asked to be the judge. And what would you do? Would you find the person innocent or guilty and explain and support your conclusion? Jen, skip to the last couple. Here's really the conclusion of it all. The policy in many countries calls for the coverage. The policy is covered in the national curriculum. And they expect teachers in all of these countries, including the US, to cover content in these other dimensions. They want to achieve literacy, but the preliminary observations are that the books just don't support it. So there's a profound disconnect between the policy issues and the practice as reflected by the textbooks. The next slide. And this really is what, in the end, it comes to. Perhaps now, and I have a 17-year-old who just says this all the time, perhaps we can understand why children just say, why do I care? How many of you have heard that? How many times? I'll never use this in real life. And I think what we need to do is to show them through this integration of real world applications, replace the word problems and use those and introduce through those reasoning of varying sorts, the 4 types, together with the more fundamental concepts that undergird these procedures, and bringing in the 21st century skills where appropriate and where they fit to be brought in. And let me just show you one other problem. Back up, Jen. Back further. By the way, just go back to that one. The one with the pictures of the, here's a good next one. There's a problem. You start out with a square and then you start putting it together in a pattern. And then on the next page, you're asked to say how you got to those patterns. You can see the reasoning that takes. You have to figure out what the unit is. that's being maneuvered and manipulated in order to get to different shapes. And I'll give you my last and one of my favorite ones. I think it's the next one up. Next, yep. You got 100 years of history. The bears just love to come to the city dump and eat the garbage, and people love to come and observe them. And you know, you're told one day they were there yesterday, so you decide not to go to observe for the next 4 days. Is that a wise decision? Why? Is it or isn't it? How would you time your trip? It calls for a clear understanding of probability. And so I think you get the idea of the real world applications, the higher order real world applications have to challenge them to even figure out what the question is, and then to find the relevant information and to apply it to try to find the solution to it. And so I leave that thought with you, that I think that the world needs mathematics literacy if we're going to give all children in the world a chance, no matter their background. We need them to be able to understand these things so that they cannot be buffaloed and confused by various dresses, various movements, that they can actually reason their way and make a sense of what the world is doing. And no better example than this pandemic. So we need this. We need every kid to have this. And the only way we're going to do it is to have and to change those books, get rid of those word problems and put problems like this, which they won't do 10 of per night. They may do 1, and they are beautiful for discussion. And also I think they could be considered for examination questions as well. Thank you very much. I hope this is helpful to your thinking about reasoning and the world of applications.
Thank you, Bill. This was terrific.